Hi everyone, thanks for having me. And it's my honor to speak here. And my topic today is a recent paper called An Interpretable and Simplification Deep Kernel for Gaussian Process. My name is Yijue. Okay, and so we all know there are two technical issues when we develop a Gaussian process model. The first is the scalability, since the original model has the O and cube complexity, okay? And another one is the optimal kernel design. So our paper is following this direction, since if you choose a good kernel functions, that will leave the raw features to a high dimensional space. So in that space, the regression and classification problems will be more effective and easy to solve. And there are a lot of related workings recent years. The state-of-the-art works can be concluded in the following three categories. The first one is the multiple kernel learning, which is just like a linear or nonlinear combination of some primitive kernels, and through some specific optimization. The goal is to let the data to determine the best kernel configuration. Okay, and the main drawbacks is that we need to subjectively select the primitive kernels and also the weights for each kernels. Okay, and another famous category is the spectral kernel learning, which is to approximate the spectral density of a desired stationary kernel by a mixture of basis functions, right? And now the famous one, deep kernel learning, like the Wilson 2016. So we can further divide it into two classes. The first one is that you just directly embedding the neural networks to the primitive GP kernels. Another one is to you mimics the learning dynamics of the neural networks by the GP models. Okay, so as we know that the deep neural networks is kind of interpretable models, and a lot of people working in the interpretable deep neural networks. So if you combine these two, the model interpretability will definitely lose some. And if you want to train the deep neural networks well, you need a lot of training samples, right? So, and in our paper, we proposed a novel deep kernels that can improve the following four aspects called optimal, interpretable, simplification, and then robust. And we will see more details in the next pages. Okay, so for classification and the regression problems, if you want a minimum test means for error between the two labels and the predictions, and we proposed a theorem, this optimal kernel matrix theorems that can guarantee there is optimal kernel functions. Okay, it's this equation one is just a dot product between the underlying function this fx, but the underlying function fx is we don't know, and we need to estimate these functions. Okay, so in this paper we're using deep neural networks to directly universal approximate the underlying function fx. So now we have our equation 2. So this OK optimal kernel. As we can see, this gxw is a universal approximator of the underlying function fx. Okay, and this xw is also the output of the deep neural networks. The most advantages of this kind of kernel is that you can see this kernel is just parameterized by neural networks weights. We don't need other kernel parameters like the length scales or noise or something, right? Okay, and we further want to improve the model interpretability and the simplification and robust and something. So we further propose the generalized additive model based on this equation 2. We can see this equation 3. Now we have this IOK kernel, interpretable optimal kernels. So we can see the original GXW, this mapping is further divided to K parts. So here we applied some future interaction detection methods. After this detection method, we can often K interaction sets. So for example, if here this X set 1 is this S1. So for example, if the S1 is combined by the inputs X1 and X2, so the sample X1 X2, so it means there exists strong interactions among the two inputs, okay? So, and we can construct K subnetworks, which is much smaller than the original bigger deep neural networks, okay? Now we can see the kernel structures of our IOK kernels. This one is the OK kernels. We have a big deep neural networks, and now we divide it to K subnetworks. So you can think this way: subnetworks have much less layers and neurons, so it requires much less sample training samples, right, and much much less parameters to estimate. And as we obtain this inputs for each subset is the interaction set. So we assume this strong interactions will give us good data feedings. It means each subnetworks, each output of the subnetworks will give us a good data feedings compared to the original bigger one. Okay, this is our idea. And now we can see some simulation results. This is for the real regression data sets. And we can see our proposed OK and IOK kernels will give us the best performance compared to the deep kernel learning with some primitive kernels. This DNA is a pure deep neural networks. And this is robust test. As we can see, we repeat this experiment. And the yellow one is our proposed kernels will more robust than the deep kernel learning with RBF kernels. This one shows that the bottom one shows that our kernel is still robust too when we are reducing the person of data training. And this one is very interesting as we also simulate our work on the synthetic data. And so we can see F3X is the underlying functions. This figure 1 and figure 2 is the first two subnetworks output, and we can see this output of the subnetworks is very good. So I think this you can see for the real data set we have this mapping, and this is very helpful for the experts to find information behind the data, the real data. Okay. So in summary, we proposed an optimal yet explainable and efficient deep kernels, and there is one advantage is that each subnetwork can parallel training on different GPUs or Spark or anything else tools, and we can put the highways to pivotal subnetworks. Okay, like that we have winning tickets in the final win tickets to the deep neural networks. Okay, and then some references, and thank you for attention.